So in this class we will start with the igneous petrology. So it is one of the most important topic, as we all know. So igneous petrology we will cover for GATE and GSI. So I will cover both for pre and mains. So this is a detailed lecture on this. So we'll start with the first topic, that is generation of magma. So how magma is generated? Magma can be generated by in the crust, in the mantle, and in the outer core. So in the crust, we know that the crust is basically solid in nature. So how the magma will generate? By the process known as crustal anastasis. Okay. So what is this anastasis? Anastasis means partial melting of the crust. Means suppose if the crust is there, here is this part. So if suppose this is the crust here, and from beneath, if the magma is coming like this, magma is coming like this. So what it will cause? It will cause the partial melting of this region. Okay, this will cause partial melting of this region. So partial melting of crust is known as your anastasis process. It will produce the magma which are granitic in nature. This is very important. The crustal anastasis process will produce the magma which is of granitic composition. Now another through mantle, which is solid in nature. Here also magma is generated by 1 to 5% of the partial melting in the low velocity zone. Okay, low velocity zone. This low velocity zone is present at around 150 to 200 kilometer, and it is a part of upper mantle. In outer core also magma is generated, and as we know, outer core is liquid in nature and composition is basically iron, nickel, and cobalt. Now majority of our magma is produced where? It is produced in the mantle. Okay, so majority of the magma is produced in mantle. Now what is partial melting? So in partial melting, what happens? Your rock is there, and as we know, this rock does not melt at once. So slowly and slowly this rock will melt. So when suppose a rock is there, let's say this rock is there, and its melting starts. Okay, so this rock is there and its melting starts. So this rock will break into two parts, that is solid and liquid. So this liquid which is produced here, this is known as residual liquid, and this residual liquid, it will be more mafic. This residual liquid will be more mafic. No, sorry, this residual liquid here, this residual liquid will be more felsic. This will be more felsic. How? So as we, if you go and see the Bowen's reaction series here, now see, as we see the Bowen's reaction series, first olivine crystallizes, then pyroxene, then amphibolt, then biotite, then here feldspar, then muscovite, and after that quartz. So this is the order of crystallization. This is the order of crystallization here. This is the order of crystallization. Now what will be the order of melting? It will be exactly opposite of this. This will be the order of melting. So therefore, if any rock is there, and if the partial melting is happening in this rock, if the partial melting is happening in this rock, so it will become what you will get another solid and a residual magma. So as the temperature is less, okay, temperature is less of what? This quartz at which it melts. So here the temperature is less of whatever minerals whose temperature is less, it will melt first. So therefore this residual magma will be rich in your silica content. And therefore this residual magma will be more felsic. And this solid, left solid, it will be more mafic. So this is very simple to understand from here, the concept of partial melting. So as partial melting happens, what we get? We get a residual rock and we get a magma. So the magma which is produced will be more felsic. Just now I have explained that. And the residual rock which left will be more mafic. So after the partial melting of the parent rock, residual rock will be more mafic and the magma generated, it will be more felsic. So this is the entire concept how the magma is generated. Now the another term comes which is known as liquidus. So what is liquidus? The temperature at which crystallization starts. So this is the temperature at which your first crystal will start to form. Means here temperature at which you can also say your melting is finished. Now same with the solidus also. Solidus is a temperature where melting starts. Okay, means here the entire solid will there and the first drop of melt will come when it hits the solidus curve. Now the temperature at which the crystallization is finished, we can say like that. The next term is geothermal gradient. So what is geothermal gradient? The change in temperature with respect to depth. Okay, it is given by degrees Celsius per kilometer. In upper crust it is around 25 degree Celsius per kilometer and geothermal gradient increases with increase in depth. Now this is the temperature versus depth graph. It is important for GSI. Now as you can see, this is the portion for, this is our lithosphere, this region. So here the geothermal gradient will be around 20 to 25 degrees Celsius per kilometer. So here you can see in the blue color how the geothermal gradient is increasing with increasing depth. With pencil I have drawn the solidus curve. So if this geothermal gradient, this is important to understand here, if this geothermal gradient will cross this solidus curve, okay, solidus is a point from where melting starts. So if this geothermal gradient by any process will cross this solidus curve, then only melting will begin. Okay, so if geothermal gradient crosses the solidus, melting will start. So this solidus curve is of, this is for crust, this is for astronosphere and same for outer core here. So here you can see in this portion, this D double dash layer portion here. So here your geothermal gradient is crossing the solidus curve. So D double dash layer produces most of the magma. So this D double dash layer here is the main reason of magma generation. This is the main reason of magma generation. And where it is present? It is present just above the outer core. Okay, it is present just above the outer core. So now under general condition, actual temperature is greater than the solidus temperature in general condition. So therefore there will be no melting. Okay, because for the melting your geothermal gradient should exceed the solidus temperature. This is for temperature. Now, so melting will take place when your geothermal gradient should be greater than the solidus. So how this possible means this geothermal gradient here, this geothermal gradient, if it exceeds the solidus temperature like this, then only melting will begin. Then only melting will occur. नहीं तो melting नहीं होगी. अगर टेम्परेचर सॉलिडस को क्रॉस नहीं करेगा तो मेल्टिंग नहीं होगी. देन देयर विल बी नो मेल्टिंग. सो हाउ दिस इज पॉसिबल? If you increase the geothermal temperature at a given depth, or if we decrease the solidus temperature, solidus melting point, or these are the two reasons. So how you can increase the geothermal gradient? First is the presence of the radioactive isotopes like potassium, thorium, uranium, or due to frictional heating, or due to convection of mantle or decompression melting. Now we will see all this in detail. Now generation, this all this will come in detail in the next pages. Now generation of magma. What is magma? It is a molten rock inside the earth. Rock does not melt at a single temperature, this I have already told, but over a range of temperature. Solidus we have seen what is solidus, liquidus also we have seen what is liquidus. Geothermal gradient also we have seen. Now this curve is important here. So in the y-axis it is the depth, in x-axis it is the temperature. So this is our geothermal gradient here. This is our geothermal gradient, this one. This one is here is the solidus temperature. And here this is a liquidus temperature, means here 100% melt will be there. So if this geothermal gradient crosses the solidus, then over your melting will start. So we have seen how the melting will start. Either we will increase the geothermal gradient this point, or we will decrease the solidus. Okay. Now how you will increase the geothermal gradient? First thing is by the presence of the radioactive elements such as potassium, thorium, or uranium. So these are the main radioactive element in the earth crust. Higher concentration can possibly lead to the melting. So if this is present, if these radioactive elements are present, what they will do? They will increase the geothermal gradient. And if this geothermal gradient is increased, now normal geothermal gradient is like this, and our suppose solidus temperature is somewhat like this. This is the solidus temperature. Now if this geothermal gradient is present, what it will do? It will increase the, if this radioactive element is present, it will increase the geothermal gradient. It will increase the geothermal gradient, and if this geothermal gradient will increase, our melting will start at this point. At this depth, our melting will start. So melting will begin here. Melting will start. So this is the first cause. Second is frictional heating. Now frictional heating is due to the fault motion. You have heard this term pseudotechnites also, which are formed in the due to frictional heating. This question came in GSI prelims. So these pseudotechnites these are formed due to frictional heating. So this, because of this friction, huge amount of heat is produced during the faulting, and it can result in your heat and melt. However, very low quantity, this is important to understand, very low quantity of molten rocks can be generated by this process. Another is decompression melting. So what is this decompression melting? As you can see here, this magma here, it rises up, okay, and it increases the temperature of this crust nearby here. So it will increase the temperature here. So this mantle convection can carry heat from the lower part to the shallower part and thus increasing the geothermal gradient. So this is our normal solidus curve here, and because of this decompression melting, means because of the rising plume, that because of this convection current, your geothermal gradient is basically increased here. This portion, this is the elevated geothermal gradient. Why? Because of decompression melting. Okay, so here this portion here, your magma will start to generate. Magma will start to generate. And this basically you see this decompression melting in the area of mid-oceanic ridges. Now how you will, so this is the few reasons of increasing the geothermal gradient. So how you will increase the geothermal gradient? So we have seen increase of geothermal gradient. So how we can increase? First was we have seen if the radioactive source are present. Second method we have seen is the frictional heating. And third we have seen is the decompression melting. And this decompression melting we generally see in your mid-oceanic ridges. Now the second thing which we can do is the graph was like that. So this was our depth and here was the temperature, and here is our normal geothermal gradient. So this is our normal geothermal gradient. Now suppose this is the solidus here. Now if suppose you decrease this solidus, if suppose if we decrease this solidus like this, okay, so if we decrease this solidus like this, then also you can see the geothermal gradient is crossing the solidus curve, then also melting will generate. So if you decrease the solidus like this, then also your melting will start. And how this is possible? You can decrease this solidus by adding the volatile fluxes, volatile flux like your water. So this can happen where? In the area of subduction zones. So here by addition of the volatile flux by the subducting slab at the convergent plate boundary can lower the solidus. Okay, so in subduction what happens? Presence of water is there or volatile flux is there, it reduces the solidus. Now in this graph we can see this is our normal geothermal gradient here, and here the solidus has reduced. Okay, so this is the temperature here and this is the depth. So here the solidus is reduced. This is the original solidus curve. So here we have completed our topic, that is generation of magma.